What's up everyone, welcome back. Patrick here, moving on to another word problem dealing with linear optimization. This is going to be another hectic one, lots going on here. I did go through another one before this, so I'm assuming you've watched that. So maybe with this one, I'll go through things a little bit quicker, but still I'm going to go into lots of detail. So if you're comfortable, like I mentioned in the other one, with this kind of problem, maybe you want to try it on your own and then just go to the end, check your answers. But if you're new to this topic or if you're still struggling with these kinds of problems, it might be worth it for you to watch the whole video and see in detail my process as I go about it. So let's see what's going on here. So we're told that each unit of food A contains 3 units of carbs, 2 units of protein, and 3 units of fat. Each unit of food B contains 3 units of carbs, 4 units of protein, and 2 units of fat. A diet requires at least 60 units, 50 units, and 48 units of carbs, protein, and fat respectively. If each unit of food A and B costs $1.80 and $3 respectively, how many units of each food should be purchased to minimize costs while meeting diet requirements? Okay, so as usual, lots going on here. So first thing I like to do is define my variables, and as I mentioned in the problem before, I like to get my variables with basically what they're asking us for. So notice that what they're asking us for, how many units of each food should be purchased to minimize cost while meeting diet requirements. So how many units of each food, and how many foods are there? Well, there's food A and food B. So what I'm going to do is I'm going to let X equal the number of units of food A, and Y is going to be the number of units of food B, like that, right? So those are going to be our variables. That is what they are asking us for. And then they give us information about each of these foods here. So we're told that each unit of food A contains 3 units of carbs, 2 units of protein, 3 units of fat. So what I'm going to do is I'm going to create a chart here because I feel like it's a lot nicer to get this information into a chart. It's a lot more visually appealing and it's a lot easier to look at versus going through the paragraph throughout the whole question. So, okay, we got food A, and we're told information about each of these foods with the number of units of carbs they have, protein, and fat, like that. Okay, so each unit of food A contains 3 units of carbs, 2 units of protein, and 3 units of fat, like that. Each unit of food B contains 3 units of carbs, 4 units of protein, and then 2 units of fat, like that. Okay, next sentence. A diet requires at least, so that's important right there. I'll come back to that. So a diet requires at least 60 units, 50 units, and 48 units of carbs, protein, and fat, respectively, right? So we have a minimum requirement of carbs, protein, and fat, right? So let's write this as the requirement. So what's the requirement for the carbs? Well, it's going to be 60 units of carbs. For the protein, it is 50 units. And then for the fat, it is the 48 units, like that. And then we're told that each unit of food A and food B costs $1.80 and $3. So let's put a new row here for the cost. The cost of food A is going to be $1.80. And then the cost of food B for each unit of food B is going to be $3, like that. Right? And basically we took all of this information here in the paragraph and made it into a nice chart that we can now refer to instead of going through the paragraph. So now let's take this chart and try to create our equations, our constraints. So remember, what we're trying to do is we're trying to minimize the cost, right? We're trying to minimize our total cost. So our minimizing function is going to come from this row over here. So we want to minimize our cost. Let's put that as a variable c. So we're trying to minimize cost, which is equal to, well, each unit of food A costs $1.80. So the total cost coming from food A is going to be $1.80 per unit times the number of units of A, which is x plus 3y, like that. Right? So that's going to represent the total cost right there, and we are trying to minimize that. Now, what are going to be our constraints here? So our constraints we're going to get from these rows here for the carbs, protein, and fat. Now, here's where that at least wording is important, because they're saying that you have to get at least 60 units of carbs, 50 units of protein, 48 units of fat, at least. So that means that the amount that we get has to be greater than or equal to the 60, greater than or equal to the 50, greater than or equal to the 48. So the signs for the constraints in this particular problem are going to be greater than or equal to, because we have to get at least these amounts, right? So this is where the wording is super important. If they were saying it's at most, then it would be less than or equal to, right? But they're saying at least, so that's the minimum that we have to get. So it has to be greater than or equal to 60, etc., etc. So what's the total carbs, right? What are the total carbs going to be if we have x units of A and y units of B? Well, it's going to be 3x units of carbs in total from food A, right? The number of carbs per unit times the number of units of food A plus 3y, right? Because the number of units of A is x, number of units of B is y. So 3x plus 3y has to be greater than or equal to 60, like that. And then 2x for the protein, 2x plus 4y has to be greater than or equal to 50. And then 3x plus 2y has to be greater than or equal to 48, like that, for the requirement of the fat, right? So the total fat that we're going to have to get is going to have to be greater than or equal to 48. Yeah, and then I think we're good. And then obviously the x and the y, those have to be greater than or equal to 0, right? You can't have negative units of these foods over here, right? So that's basically it. And so now notice that it just becomes an abstract linear optimization problem. All we have to do is basically focus on this part, right? We could forget about the word problem. We don't need the word problem anymore. Maybe again for our last concluding statement, when we have to refer to what we made the variables equal to, but now you just treat this as an abstract linear optimization problem, right? So this is our minimizing function, trying to minimize the costs. These are our constraints, and they have to be greater than or equal to, because that was the minimum requirement for the diet. So the next step that I'm going to do is let's graph our lines here and get what our feasible region is going to be. So what we want to do is we want to go through each of these lines one by one and graph them. And so to do that, I'm going to figure out what the x and the y intercepts are. I think that's the best way to graph them. So starting with this line, we got the 3x plus 3y. Let's forget about this sign for now and just make it equal to 60. So if we're solving for our x-intercept, plug in 0 for y. So we'll have 3x equals 60, divide both sides by 3, we get 20. So 20 and 0 is the x-intercept. Same thing for the y-intercept, right? Because if we plug in 0 for x, 3y equals 60, that means y is equal to 20, like that. Okay, next line, this one right here. So we got 2x plus 4y is equal to 50. So if we plug in 0 for y, we'll have 2x is equal to 50, meaning that our x-intercept is 25. Plug in 0 for x to get the y-intercept, 4y equals 50, divide by 4, we would get 12.5, like that. And then for this line, right here. Let's make it in green. As I mentioned in the previous problem, if you can, it's good to work with these lines if you have different colored pens, right? So then when you graph the lines, you could see clearly which lines are intersecting and whatnot. If they're all the same color, it kind of gets a little hectic. So if you can have different colors, that's helpful for each line. So what's the x-intercept going to be? Plug in 0 for y, 3x equals 48, so that means 16 and 0. And then 0 for x, the y-intercept would be 24 for this line right here. And so then what we want to do is just take these lines and graph them. So going into graphing these lines here, I made a Cartesian plane here, and I'm going up by 5s on both the x-axis and the y-axis. I mentioned this in the problem before. Try to make this as to scale as possible. So having even spaces in between, making sure the scale goes up by the same amount. Try to space it out as much as you can where it's going to include these intercepts, because when we graph the lines, you can clearly see what the feasible region is going to be, and then you know which points of intersection you have to find and which points of intersection you don't have to find and you don't have to waste time with, right? So creating as much of a scale to graph does help. So let's start off with this first line. So this first line has x and y intercepts of 20. So we're going to start right here, 20. Moving on to this next line, the blue line. So we have an x-intercept of 25 and a y-intercept of 12.5. So the y-intercept is 12.5, which is right in the middle here, and then 25. That's going to be all the way out there. And then finally, this always happens. Okay, this green line, we have an x-intercept of 16 and a y-intercept of 24. So 24 y-intercept is like up here. And then we have an x-intercept of 16. See, like, you see where there's like a lot of points here that are very close. So this is where that to scale stuff helps. And then at this point as well, when you're creating these feasible regions, maybe with other word problems, before you go into finding the vertices, maybe you can graph it and then check these lines on Desmos and make sure you get the same feasible region, right? Just so you're not wasting time and then you have to go back and check your lines, right? So graph them and then graph them on Desmos and then make sure that your lines are the same and it looks the same. And so that's going to be it, right? That's going to be the lines graphed here. And so now what we need is to define the vertices of the feasible region. Now, what's the feasible region going to be? If you remember, so now this is where the signs are important. We got to bring back those inequality signs. All of these were greater than or equal to, right? So basically, our region has to be to the right of all of these lines, right? There can't be any region where we're to the left of any of the lines. And so notice that the region is basically this over here, right? That region is going to be to the right of the blue line, red line, and the green line. However, because we're trying to minimize the cost, all we have to do is test this vertice, which is the point of intersection between the red line and the green line, and then the red line and the blue line, and then this vertice over here. Because any other point out here in the feasible region is just going to increase this cost, right? And we're trying to minimize the cost. So we want to try to get the leftmost points where we're not going to break the constraints of the lines, where these points are not going to be to the left of any of the lines, right? So for example, we can't use this point right here. Why? Well, it satisfies the blue and the green line, but notice that it's to the left of the red line. So that's not going to work, right? Because it's not going to meet that constraint for, I think this was the carbs, right? It's not going to be at least greater than or equal to 60. It has to be to the right of all of these lines. Okay, so that point right there is not going to work, right? This region here is not going to work. It satisfies the blue and the red, right? It's to the right of those, but it's to the left of the green, right? This region here, it's not going to work. It's greater than the green, greater than the red, but it's less than the blue, right? So it has to be to the right of all of the lines, and so basically it's this area right here. But of that area, we want to test our leftmost points because we're trying to minimize our costs. So it would be this point, this point, this point, and that point. And so now let's get the coordinates of these 4 points here. So this one right here, that's the y-intercept of the green line, which is 0 and 24. So that's going to be a point we have to test. And then this point here is the x-intercept of the blue line, which is the 25 and 0. So we're going to have to test that. And now what we have to do is find these 2 points of intersection, right? So again, I mentioned this in the other problem as well. This is the benefit of making your graph as to scale as possible, because we could tell that we don't have to waste time finding this point, the intersection between the green and the blue line. And if your graph is not to scale, sometimes the lines might be off and you might get a point that you think is in the feasible region, but if you made the graph to scale, or if you saw in decimals, it actually wouldn't be, right? So try to make your graphs as to scale as possible so you know which points not to waste your time with. So we are going to have to find the point of intersection between the green line and the red line, right? So between 3x plus 3y is equal to 60, and 3x plus 2y is equal to 48. Different ways you could do this. I'm noticing that I got 3x and 3x, so let's actually isolate for the 3x. So I'll have 60 minus 3y. I'm going to plug in that for the entire 3x expression. So I'll have 60 minus 3y plus 2y is equal to 48. This will be negative y, bring it over, positive y, 12, right? So y would be 12. Plug that in here. We'll have 3x is equal to 60 minus 36, which is what, 24? So x would be 8, right? So this point of intersection here is 8 and 12. And then also another benefit of making it to scale, does 8 and 12 make sense on this graph? Yeah, it's about 8. It's about 12, right? So we could be fairly confident that that is the correct point of intersection. You could take that point, plug it into the 2 original lines, make sure left side equals right side if you want more certainty, but that is the point of intersection right there. And now between the red line and the blue line, so this point here, so the red line, it's the 3x plus 3y equals 60 again, and then the blue line is the 2x plus 4y is equal to 50, right? So here, again, different ways you could do this. So you could try it your way. Just make sure you're getting the same values. I'm going to divide everything by 3 here. So x plus y is equal to 20. That simplifies. I'm going to divide everything by 2 here. So that means x plus 2y is equal to 25. And then let's maybe do elimination here. So I'm going to put this equation below this one. And I'm going to subtract it, right? So x minus x is 0, 2y minus y is y, 25 minus 20 is 5. So we get a y value of 5, plug it back in here, so that means x plus 5 equals 20. That means x is equal to 50. So this point of intersection here is going to be 15 and 5, and it's pretty much right on, right? You can't tell if it's not graphing paper. If it was graphing paper, you could tell that it would be right on the edge there. So yeah, these are the 4 points that we're going to have to test with this cost and see which of these give us that minimum cost. And so if we take those points, plug it in for x and y for our cost function, these are the different costs. We would get $72, $45, $50.40, and $42. So between these, which is the lowest cost? This one right here, the $42, right? And so that's going to happen if we purchase 15 units of food A and 5 units of food B. That's going to give us that minimum cost of $42, and it's still going to meet those diet requirements for the carbs, protein, and fat. And that is the end of the video. Hopefully you enjoyed that. If you want to find more videos like this, you can go to my website, allthingsmathematics.com. Over there, all my courses are organized for both high school and university. All the videos are organized by chapter. Also, if you have any questions, you can hit me up. My contact details are also on the website. Enjoy your day, and I'll catch you in the next one. Peace out.